What are we using in JavaScript? We're going to find out now what is those brackets in JavaScript? Does anyone have a guess what it is?
They're just something that looks interesting. Put it on the wall.
It just looks interesting? Yeah, it is interesting. I accept that. Interesting is part one. Frustrating? Could be. No guesses?
Is it an
array list?
Array list, yeah.
Array list. Great guess. I will tell you if you're right or wrong because we're going to find out empirically. So I did write this little. I didn't know where to put it, so I just put it right in this kata thing. So you can even follow along if you want to. All we're going to do here is we're going to simply create an array. Right? It's just a number array. I'm going to be able to measure a function. We're measuring in milliseconds. We don't really care. It's not super precise. We just want to get a gauge of how fast or how slow these things are. Right? So no hardcore testing here. So I create a function that simply will unshift a certain amount of times. Right? Unshift in JavaScript, remember, that's adding to a list. Thank you, Brendan, for that one. Shift, of course, is removing from the beginning of a list. So we're just going to do that amount of times. We have push, exact same thing. Pop, exact same thing. So hopefully we all see exactly how that works. Very, very simple functions. Just push, pop, shift, unshift a number amount of times. Lastly, we're going to have get based on index. So just in case it is a linked list underneath the hood, if we were to get progressively larger indices, we should see a slowdown that keeps on. We should see a linear slowdown, right? So then I create this thing, just some little, some higher order function nonsense. I can push it. I can create something that will just have the same function that calls push with the same count every time, right? So I can call it over and over again. I don't even know why I did it this way, but it just feels like it was a great way to do things at the time. I can't even remember what code comes down below. Lastly, we're going to test with 10 elements, 100 elements, 1,000, 10,000, 100,000, a million. Whenever you're doing performance testing, a little tip is you should always do a stepladder type approach. That way you can see how it grows. You can really actually run, like, say, a linear regression and say, hey, this is kind of more what I'm seeing right here. It's not it doesn't always work exactly. Right, so there you go. So you can see for every test I'm going to do, I'm going to push in the value, and then I'm going to do a get at the last element. So if indexing is linear, we should see a slowdown as the array gets bigger, correct? Correct, right? It should be 10x slower effectively every single 10x times some constant. Pushing, exact same thing. We're going to push 1,000 items after growing it to a certain length. So first we're going to grow it to 10. we're going to grow to 100, we're going to grow to 1,000, 10,000, 100,000, a million, 10 million, and then at each one of those points push in 1,000 items. If push is based on the amount of items within the array, we should theoretically see a slowdown that happens. Right? It should be linearly getting slower at every single step. Same thing with pop, exact same item, same thing with shift, unshift, and the exact same thing with shift. If any of these are linear based, as we increase the size of our array by a factor of 10, we should see a great slowdown in any of these. And so that way we can kind of test all the operations, and at that point we should be able to empirically know what type of list are we using. All right, let's do this. Source. I did it in TypeScript. npx ts node. So what do we see here? Well, notice that get really didn't matter the size of the array, right? It was always super duper fast. Push didn't really matter. Pop didn't really matter. Unshift, you'll notice it just got really, really slow. We're not even done yet. It just got horribly slow at some point. And so what are we seeing here? Well, we're seeing all of these effectively constant time operations. And there we go. Awesome. And we're seeing shift and unshift grow. It actually looks like it's effectively a 30x growth or something like that. But we'd call that a linear growth. I would call that a linear growth at that point. 10x the array, something like 10x the time it took to run. And so let's just write that out. So if get is O of 1, if push / pop is O of 1, and unshift appears to be something like O of n, we were correct in saying it's probably an array list. Right? That is effectively what we're seeing here. We're seeing instant access. We're seeing instant pushing and popping at the end. We're seeing linear shifting and unshifting, or in QDQ. And a reason, of course, we can now reason in our head the exact reason why. Underneath the hood, what is happening? 0 to n. You're shifting over n elements, however that many is. I had 10 million at one point. That should take a long time. If I had to do that 1,000 times, you can see it took multiple seconds on my computer just to execute. That's a real problem, right? Right. So hopefully this was actually a cool moment. I was really hoping that this would kind of culminate in a cool moment where we really understand all the different types of lists there are, and then we can empirically look at something in which we don't even know what the execution is, but we're able to suss out likely what it actually is underneath the hood. And so, was I correct in saying that what happened if I told you const A is not an array? Yes, Morpheus, the answer is it is definitely not, and it is an array list. Awesome. I hope everyone's awesome. I always was very curious why they didn't use a double-ended ring buffer. I'm sure there's a great reason why. I just don't know why, but I'm sure there's a great reason why that doesn't happen. All right, is there any questions at this point? Because I feel like it's a good, I think the next slide is actually, yeah, anything unclear? We're kind of ending the list section,
One question, the unshift and shift was exponential, right?
I wouldn't put it as exponential, I'd put it as linear.
Linear, yeah, sorry, linear. So,
Oh, sorry, let me rephrase the question. Shift and unshift was exponential. No, it was linear. Sorry, keep going with the question. Just so.
it's a linear, right? The shift
Yeah.
and unshift, okay.
It's linear.
So, what's the conclusion? The question was that an array or not, right?
Yeah, was it an array or not? It's not an array because it's global. You can push and pop. It actually has a notion of an ending and a beginning. Those are all very, very different from what you would get with an array. An array does not have a capacity versus a length. An array is contiguous spot of memory, or a static array is what people often refer to them. They refer to a linked or array list as dynamic arrays, things in which you have these extra operations on top of it to be able to kind of accordion it according to what you need.
It's not an array, but what can it be?
It's an array list.
Array list.
Yes, and the kicker obviously is this right here. So for those that don't know, he asked if it's not an array, what is it? It's an array list, because we do get all these sweet operations, but we don't get this. But it does provide growing. It does provide the ability to push and pop at the end. It's keeping track of a lot of extra things underneath the hood. Therefore, you can just call this is a dynamic array or an array list.
What about slice?
Slice, well, slice is just a copy, right? He might be trying to say splice. That might be the confusion here. So slice is effectively when you do a slice on an array, and you're doing it from, say, I to j, you're just saying like I want to copy from here to here, right? Starting at I up into but not including j. So that's effectively just like a mem copy, right? So that's a linear operation. All it's going to do is just take that amount of memory, copy it to a new location, hand it to you. There you go. And so if you're using an array list underneath the hood, you could effectively copy that. You could create a copy method, right? Hey, create a new array, copy all my elements in, and then take all my state. And there you go. We have 2 lists, 2 separate copies, and now you can adjust them, right? So that would be a slice.
Is there a way that's not a copy, where it's a slice and it's...
Great question. Actually, I made a YouTube video just recently with, by the way, subscribe to my YouTube. I'm almost at 100,000 subs. Oh my goodness. No, anyways, sorry. Hit that notification bell. I've never said that. But there is actually this one thing that I really hate. I've made a video on it before, is that there is actually these things that are, it depends on what you mean by a copy. And so let's look at this. So if I go const a equals new uint 8 array, and let's create a 10 big, right? And I can go a0 equals 5, a1 equals 5, a2 equals 69 for the memes. There we go. We've appropriately done all the meming. There we go. So now if we do this and we go const b equals a dot slice, say 0 to 5, and I go b3 equals 5, if I look back at a, notice that 3 is not 5. We have done a deep copy, if you will, of the data. Does that make sense? Now, here's where things get great. Let's call it a buff equals buffer alloc, say 5. We're going to create a buffer. This is a node item. Here's the best part about it, though. Instance of uint8 array. It is a uint8 array. So by even TypeScript definition, it's a uint8 array, correct? Now we can go like this. Buff dot, I think it's set. Let's see, what is it? Oh my goodness, what are you? Is it right? I always forget these things off the top of my head. What are you? There we go. Write uint 8. There we go. Let's write uint 8 at position 0, 5. And then it's going to say this. Hey, the value offset range, blah, 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 blah. Oh, I had it backwards, of course. Write value 5, offset 0. You know, Node has always managed to be backwards on all the APIs, I swear. If we write out buffer right now, you'll see it has 5 in that first position. Awesome. So let's do the exact same experiment. Const buff2 equals buff slice 0 to 5. And go buff2, let's go like this. We can go, there we go. And then just put a buff2. So I'm going to go buff2. Let's write it at offset 3. And if I look at buff1, what just happened? Buff1 was. So this is actually a shallow slice. So buffers in Node are shallow sliced, meaning that they just simply
Welcome to Data Structures and Algorithms in JavaScript. My name is Scott Barrett, and I have taught tens of thousands of students data structures and algorithms. And my courses have some of the highest ratings on.
So our next big O notation is O of 1. So let's start out with some code here. We have a function called add items, and all we're going to do is it is essential that you understand big O when you go into a technical interview, because this will absolutely come up. Understanding this will also make you a better coder. So what is it? So think of it like this. We have two sets of code. We have code 1 and we have code 2. How do we determine which one is better? Now both of these are going to accomplish the same thing, but they're written differently. Is code 1 better? Maybe it is easier to read. Or is code 2 better? Well, maybe there are other things about that make code 2 better. Well, big O is a way to mathematically figure out which of these two is better, which one runs more efficiently. So obviously we can't measure this with a scale, so I'm going to bring in a stopwatch to make the point. Let's say we run code 1, and when we run it, we start a stopwatch, and it runs for 15 seconds. Then we reset the stopwatch, and we run code 2, and code 2 runs a lot longer than 15 seconds. Well, obviously we want our code to run as quickly as possible, be as efficient as possible. So by this measure, code 1 is the better code. This is what is called time complexity. But we don't measure time complexity in time. We measure it in the number of operations. And the reason we do that is if you took the same code and we ran it on a faster computer, obviously it would complete in less time, but the number of operations would be the same. So either way, on the fast computer or the slow computer, the time complexity would be the same. The number of operations would be the same. Also with big O, we measure what is called space complexity. And space complexity is the amount of memory that something uses. So let's say code 1, while it's very fast and runs in 15 seconds, or comparatively fast, maybe it uses a lot of memory. And then we reset all of this and we look at code 2, and while that runs a really long time, the full minute, maybe it uses less memory. And if this is what's most important to you, maybe code 2 is better now. We are going to look mostly at time complexity, but space complexity will come up in interviews. They'll ask you, okay, you wrote this code in such a way, maybe during a whiteboard session or something like that. And they say, great, you've optimized for time complexity, but what if we care about space complexity more? How would you write it then? You will have to understand both concepts. But what we will focus on mostly in this course will be time complexity. So when you're dealing with this kind of notation, there are 3 Greek letters that you'll consistently see. They are omega, theta, and omicron. Omicron is better known as O, as in big O. And big O is the one, of course, that you're going to see most often. So to explain this, I'm just going to bring up an array. Let's say we're going to build a for loop to iterate through this array until we find a particular number. If we're looking for the number 1, this is our best case with the least number of iterations through the array. This would be our worst case. And 4 would be our average case. So this best case is represented with the Greek letter omega. This average case is represented with the Greek letter theta, and our worst case is represented with omicron or O. So big O is always going to be worst case. And I want to point this out because it is very common for people to say things like, okay, that's your worst case big O, but what's your best case or average case big O? Well, technically there is no best case or average case big O. That would be omega or theta. So when we measure big O, we are always measuring worst case. So now we're going to look at our first big O notation. And I start with O of n, not because it's the most efficient or least efficient, but because I think it's the one that's easiest to get your head around. So I'm going to explain this with a function. And I'm going to call this function log items, and we're just going to console log out some items. So we're going to run a for loop, and the for loop is going to run n times. And then we're going to console log out I from the for loop. And that's it. Pretty simple code. So let's go look at this in Chrome DevTools. So there is our function. We're calling it with the number 10. And let's run this. And you can see that we've console logged out 0 through 9. So let's go back over to our other screen. So this is an O of n operation. So to put it another way, we pass the function the number n, and this ran n times. So we passed it a 10, and it ran 10 times. It output 10 things. That's what O of n is. So let's take a look at this on a graph. O of n is always going to be a straight line. It is proportional. The number of operations is going to be proportional to whatever n is. So on this graph, this axis represents n. This axis represents the number of operations. Okay, so that is our first big O notation, and we'll be adding to this graph with the other big O notation so we can compare one against another. But for now, that is O of n. Big O has several ways in which we simplify the notation, and it makes things easier. The first that we're going to look at is called drop constants, or you'll see it referred to as remove constants. You'll see it both ways. So to explain this, I'm going to start by bringing up the code that we had in the last video on O of n. But I'm going to add a second for loop that's identical to the one. above, except that we're going to use j instead of I. And both of these for loops are going to run in times. So let's take a look at this in DevTools. There's our code, and we're going to call this with a number 3. Okay, so let's run this. And our output is 0, 1, 2 from the first for loop, and then once again 0, 1, 2 from the second for loop. So let's go back over here. So our code ran in plus n times, or 2n. So it would make sense to say that this is an O of 2n operation. But this is where that simplification comes in. It doesn't matter if it's 2n, 3n, or 100n. If there's a constant, we drop the constant, and we say that this code is O of n. So our first rule for simplifying our big O notation, drop constants. So now we're going to look at our next big O notation, which is O of n squared. So we're going to start this off with the code that we used in the last video, where we had a for loop followed by another for loop. But I'm going to change this, and we're going to remove the console logs, and we're going to nest one for loop inside of the other. Then our console log is going to be for I and j inside of the two for loops. So let's go over to DevTools. And there's our code, and we're going to call this with the number 10. So let's run this, and if we scroll up to the top, we start with 0, 0, and if we scroll to the bottom, we go to 99. So we output 100 items. So let's go back over here. The number of items that were output, in this case, is in times n, or n squared. And that's where we get our O of n squared. So let's take a look at this on a graph. So if we had two sets of code that accomplished the same task, and one was O of n squared, and the other is O of n, the O of n code is better, because it's going to complete the task in fewer operations. So this is our first opportunity to see how it is that we could compare one code set against another. And O of n squared is generally considered an efficient code. If you can write your code in a way that is going to become O of n, it is going to be much more efficient. So that is O of n squared. Drop non-dominance is another way that we simplify big O notation. So to explain this, bring up some code here. This is our nested for loop that we saw from before. What I'm going to add to this is an additional for loop that comes after the nested for loop. Let's take a look at this in DevTools. So there's our code, and we're going to run this with the number 10. Okay, I'm going to scroll to the top to begin with. So we have output here is 0, 0, and this goes through to 9, 9. This is our nested for loop. That second for loop that follows it goes from 0 to 9. So let's take a look at this over here. That nested for loop ran O of n squared times. The second one ran O of n times. When we add these together, this becomes O of n squared plus n. So if you think about this in terms of if n was 100, n squared would be 10,000, where the single n that's added to it in this equation is only 100 more. It's not really affecting the number of operations. N squared is the dominant term, and n by itself is the non-dominant term. So we just remove it. So we drop non-dominance. We're going to return n plus n. There's only one operation here, and that's the addition. So it doesn't matter if n is 1 or n is 1,000,000, the number of operations is going to be 1. And that is O of 1. Well, what if we add another addition? Well, now that's 2 operations, right? O of 2. And as you may have guessed, we're going to simplify this and make it O of 1. So O of 1 a lot of times is referred to as constant time. So this situation here where we have 2 additions, it's 2 operations. That is constant, no matter what n is. The number of operations does not change as n changes. So let's take a look at this on the graph. It's just a flat line across the bottom. It is the most efficient big O. Nothing is more efficient than O of 1. Remember, you will also hear this referred to as constant time. So if you hear that phrase, that is O of 1. So the last big O that we're going to look at is O of log n. So I'm going to explain this with a sorted array. And in order to do what I'm about to do here, you have to have sorted data. Let's say you want to find a number in this array. And we're going to look for the number 1. What would be the most efficient way to find that? What we're going to do here is we're going to take the array, we're going to cut it in half, and say, is the number 1 in the first half or the second half? Well, it's not in the second half, so we don't even have to look at any of those numbers. And that may not seem like a big deal when you have an array with 8 items in it. But if you have an array with 1,000,000 items in it, you just made it where you have 500,000 items that you don't have to look at. So then we do this again. We cut this in half. It's not in the second half. We're going to remove that. And then we do it again. And now we have found the number 1. This is a technique called divide and conquer. So let's bring everything back here and count the number of steps that we went through to find that item. It was 1, 2, 3. And remember, we had 8 items in the array. And 2 to the 3rd power equals 8. So I'm going to turn this into a logarithm. And if you're not a math person, don't worry. We're not going to go deep into this. But look at the 3 numbers we have here. The 2, the 3, and the 8. Log sub 2 of 8 equals 3. I'm going to back this up. And we'll look at this again. Log sub 2 of 8 equals 3. We're basically saying 2 to the what power equals 8. 2 to the what power equals 8. Well, that number is 3. To put it another way, if we take the number 8 and we repeatedly cut it in half, we divide it by 2, how many times do we have to divide it by 2 to get down to 1 item? And that is 3 times. And the real power of this is when we get to very large numbers. Let's say we have log sub 2 of this number, and this is over 1 billion. How many times would you have to cut this number in half to get down to 1 item? And that would be 31 times. To put it another way, 2 to the 31st power equals this number here that's over 1 billion. So if you had an array with 1,000,000,000 items in it, and you were going to iterate
we have offsets within this contiguous memory space in which they're actually just saying, hey, I exist between these two places. And so when you say, hey, give me a slice, I just simply adjust the indices and then still point to the same piece of memory underneath the hood. Now, obviously, the danger, of course, is where I showed you the whole, where are you?
through that array linearly to find something and say what you were looking for was the last item. You would have to look at 1,000,000,000 items to find it. But if you use divide and conquer, you could find any item in that array in 31 steps. And that is the power of O of log n. So now let's look at this on a graph and see that this is very flat. Not as flat as O of 1, of course, but very flat, very efficient compared to O of n and O of n squared. At this point, I want to show one other thing on the graph. I'm not going to talk about this in a lot of detail, but I just want to show this, and that is O of n times log n that is used in some sorting algorithms. And this is the most efficient that you can make a sorting algorithm unless you're sorting only numbers. But if you're going to sort multiple types of data, you're going to sort strings, this is as efficient as you can make a sorting algorithm. We will talk about this and how we came up with n times log n when we get to those sorting algorithms, because it'll make more sense then. So that's why I'm not going to talk about this now. I'm going to take this back out. So for the rest of the course, everything that we look at is going to different terms for inputs is the interview question. Followed by is that instead of passing this in, we're going to pass it two variables. This one is going to run a times. Well, this one is a for loop, and a single for loop is O of n. And we're going to add these together, and because you can't variables be a or whatever the variable might be. O of a plus if you actually have to use different terms for inputs. So now we're going to talk about the big O of arrays. And it's important to understand the big O of arrays. So we're going to start with an array that the important thing here, because of that, push and pop are both O of 1 operate index of 4. The important thing here, though, is that we do not have to reindex this or this or this, all important for explaining the big O of arrays. So we're going to start with an array that we've already created that we call myArray. And then we're going to push an item onto the end. So myArray.push is going to push this number 17 onto the end with that index of 4. The important thing here, though, is that we do not have to reindex this or this or this all the way down to the beginning. Likewise, when we remove this item with a pop, we pop that off, we don't have to reindex anything. And because of that, push and pop are both O of 1 operations. But it's different on the other end of the array. So let's bring up myArray, and we're going to shift that first item off of the array. When we remove this, the problem we have is that this index is incorrect. The first item in the array should be 0. So this has to be reindexed to 0. And the next item has to be reindexed, and the next item. Likewise, if we do an unshift and we bring that 11 back, we have to reindex everything in the array all the way down just to be able to bring this back. Not a big deal when we have a small array like this, but if we had one that had thousands of items, that's a lot of reindexing. So this is O of n, where n is the number of items in the array. Very important with arrays to understand that on this end, adding and removing are both O of 1. On the other end, removing, because of the reindexing, and bringing it back because of the reindexing, are both O of n. Now, let's look at adding something into the middle of this array. So we'll say my array dot splice. And if you haven't seen this before, the index of 1. This 0 means we're not going to remove any items. And this means we're going to add an item with a thing in there. And when we do, this index is incorrect. We have to reindex this and this and this all the way down. Since we have to reindex all of this, this is O of n. Now you might say, hey, we're putting that in the middle. Wouldn't that be O of 1/2 n? Well, there's two problems with that logic. First is that big O always measures worst case, not average case. The other problem is this. Even if this was a 1/2 n operation, 1/2 is a constant. And we'd remove this, we're removing somewhere in the middle of the array. That's going to be O of n. 7? No. Tell me what's as an O of 1 data structure. You're making your decision. So I just want to wrap up our section on big O. We increase in to 1,000. Is that you'll hear. So these are our big 4 that we're going to look at. Top of the B, which begins with the Greek letter omicron, or O for big O, and space complexity over here. Notice they're all the same, except for one of them, which we're not going to build in this course. But everything is O of n, except for that one. So everything that we're going to build for data structures have identical space complexities. And this is one get for a sorting algorithm. Is O of n times log n. I will also include a link to this site. This is a great resource, and I encourage you to go.
卫生部对提供脐带血存储服务的康盛人参集团部分脐带血储存罐的环境温度不达标，罐可能也暴露应对的步骤。当局将采取的步骤包括同康盛人参集团紧密合事件不重新转移到其他的脐带血中，可能因为部分的储